All right. So this one is not an example as much. You were asking about proofs. It's ironic. So there is a relationship between our linear speed and angular speed. There's a connection between the two. Okay. So let's figure out what that is. So let's start here. If I say theta is equal to the arc length divided by the radius, and then I divide both sides, or not divide both sides by r, but I want to pull that r out, so I'm going to multiply both sides by r. Okay. What happens is these r's cancel, and I get the radius times theta is equal to s. Okay. So now in algebra, I could do whatever I want as long as I do it to both sides of the equation. So what if I were to divide this by time and divide this by time? Okay. All right. Cool. Now I'm going to rewrite that. And so I'm going to rewrite this as s over t equals r times theta over t. And then also remember that my linear speed v is s over t. And that my angular speed is actually theta over t. So wherever there is a s over t, I'm going to plug in a v. And wherever there is a theta over t, I'm going to plug in omega. Okay? So what does that mean? Well, that means that the linear speed is equal to the radius I spelled radius wrong. I did with an A, it's a U. So funny. I started to write radians instead of radius. Times the angular speed. That is not good penmanship. So that's a relationship directly between the angular speed and the linear speed. Okay. So now that we know that, let's do an example problem. And I'm going to sketch. I don't know if we have time to do the whole problem or not. Maybe we'll assess that in a second. So what does this mean? Well, let's sketch out based on what's occurring. So what's going on here is that as we rotate this way, we have a change in the angle theta. That change in the angle theta over time is my angular speed. that angular speed, if it's constant, has an impact on the arc length, right? The arc length is changing as the angle is changing. So imagine this thing swooping around. As the angle changes, so does the arc length. Well, the arc length over time is the linear speed. Well, what's the proportionality of it? Well, it's the distance from the center of the circle, which is the radius. Does that make sense? So that's how we got to look at it. That's how we got to think about it. Now, tires on a car and all that stuff. So engineers use this a lot to determine the speed of the car. That's how your car knows how fast it's going. So when it says you're going 55 miles per hour, it's not like it has a radar gun like a police officer and it can actually calculate your linear speed. What it does is it counts how many rotations the tire makes, and based on the radius of the tire, right, times the angular speed. In other words, it keeps track of how many. It's basically a revolution per unit time times the radius of the tire. So what your car does have is something that tracks the revolution of the tire and the time that it takes for it to make one revolution. And through this equation, it actually calculates your linear speed. Okay. All right, so let's try to, we might have time. I'm going to try to do one example real quick. So there's a lot of stuff to write down, but I think you guys can do it. So let me copy and paste this. So a 2020 Tesla Model 3, 450 horse, or 450H is the actual model number. I don't know why I said 450H. Comes standard with wheels that have a rim diameter of 18 inches and a tire diameter of 28 inches. If the owner decided to upgrade the wheels in the rim of 20 inches to a diameter of 30 inches without having an onboard computer updated, how fast will the car actually be traveling when the speedometer reads 75 miles per hour? So this one is a little more challenging. So what we need to do is let's think about the relationship here. So the first thing we need to do is write the formula for the relationship between the linear speed, the radius, and the angular speed. And then what I want to do is I want to divide by the radius. So I get that the linear speed divided by the radius is equal to the angular speed, because that's what I want to figure out is the angular speed. Well, what did they give us? Well, they did give us a radius, sort of, right? That's the information that we have. We have a bunch of radiuses, right? We have 20, and we have 30, and then we have 28, 18 inches. So we got to figure out exactly, that's the tire diameter. So really, we're probably going to do the tire diameter, okay? So, but the rim might play into it too. So then what does that mean? Well, that means that our angular speed is 75 miles per hour. Okay. And if the diameter of the tire is 28 inches, then the radius is the diameter divided by 2. In other words, we would say 28 inches divided by 2 is 14 inches. So right now I'm figuring out the angular speed of the car without the modification. Sorry, I probably should have clarified that first. So we're going to divide that by 14 inches, right? So then when I do the math on that, I need to convert that to inches. So to convert to inches, this is an interesting thing. 1 mile. 1 mile is equal to how many feet? How many of you guys know that off the top of your head? 5,200.
5,280.
Very good.
I remember
Feet, right? And then, good job. And then 1 foot is equal to 12 inches. Now, if you crank through and you do all the math, it's actually 63,360 inches. So then this becomes 75 times 63,360 inches per hour over 14 inches. And the reason we wanted to put the inches in there is because we're going to cancel the inches. Inches divided by inches. And so when you crank through the math on this, we'll get that the angular speed is 330, when you do all this math, radians, 333,429 radians per hour. Cool. So now that I know the angular speed, I just need to go back and say, okay, well, now let's figure out what that is with the new radius. Does that make sense? All right, so the new radius is 30 inches divided by 2. So the new radius is 30 divided by 2, which is 15. So I'm going to say 15 inches, right, times the angular speed, right, which is, which is 339,000 times 429 radians per hour. And so what that gives me is an angular speed of 5,091,435 inches in an hour. But now I've got to convert that. Remember that there are 63,360 inches in 1 mile. Right? The inches cancel, and when you do the math on that, it's about 80 miles per hour. So let's do the approximation. So by changing the size of the tires by 2 inches changes the linear speed by 5 miles per hour. That's why they want you to come in and update the software, because the software does all this math. Okay? Any questions on that one? Let me zoom out so you guys could see it a